Section 7.1, sine, cosine, and tangent graphs. In the first activity, you guys are going to graph sine and cosine. So you're going to begin by using the unit circle to complete the t-tables for each function. And this should be pretty quick since you should know the unit circle by now. And then you're going to plot the points from the t-tables onto the coordinate planes. So just for instance, for the first one, y equals the sine of x. So we're saying x is 0, so the sine of 0 would be 0. And if we did these pi over 6 for x, we would have the sine of pi over 6. So the sine of pi over 6 we know is equal to 1/2. And then we get root 2 over 2. And then we get root 3 over 2. And then we get 1. So those would be the first points that you would graph. So we'd have the sine is of 0, 0. Pi over 6 is 1/2. Then we get pi over 4, root 2 over 2, pi over 3, root 3 over 2, and then pi over 2, 1. So you're going to continue that for all of these numbers. And you're going to do the same thing for cosine. And then you're going to, after you do all that, in a different color, complete the graph for the coterminal angles up to 4 pi. So pause it and then come back and then check your answer. So when you graph the sine, notice that this is what you get, and notice that our curves are smooth and rounded when we make them. And for our coterminal angles, when we were graphing them, so I started at 13 pi over 6, so I know the sine of 13 pi over 6 is coterminal with pi over 6, so that's how I got the 1/2. 9 pi over 4 is coterminal with pi over 4 right there, so that's how I got that point. 7 pi over 3 is coterminal with pi over 3. And then I know 5 pi over 2 is coterminal with pi over 2, so that's how I got this point up here. And you notice that the points are going to keep on repeating themselves. And this is important because this kind of helps us show that we could keep going around and around on our circle, and we would end up getting the same answers for coterminal angles. And because of that, we know our domains from -infinity to infinity. And if you look at your maximum point here, the maximum point is at pi over 2 comma 1, and we have a minimum here at 3 pi over 2 comma -1, so we know our range is in between -1 and 1. And that range part that we actually have what's called an amplitude, which we'll talk about a little bit later, and the amplitude is half the distance between the max and min points, and so in this case that part would be the amplitude of your graph, and of course it also works for the bottom, the negative part of your graph as well. Now for this is our sine parent graph, and of course it goes backwards and keeps repeating, and this first part right here, from all the way from 0 to we get to 2 pi, before it starts repeating, that's what we call one wavelength or one period of our graph. So this would be the first wavelength, and usually when we're graphing these we always start with 0, 0 and move our graph from there. So then the same thing happens for cosine. So for the cosine graph, except for you'll notice that the difference between sine and cosine is that the cosine graph starts at a value of 1 and then moves downward. And for the cosine first graph that we have, we start up here and we move down from our function, and that would give us the first wavelength, and then this next part over here would be the second wavelength for cosine. So this is what our parent graph looks like, and of course we could continue on the right or we can continue on the negative side, and we'll talk about that a little bit more. And because of that, we know that again the domain is from -infinity to infinity because we have infinite amount of many angles we can plug in, and our range is from -1 to 1. Now the first wavelength is usually what we start with, and then we move things around from there. So for this, again, the amplitude would still be the same, which is a value of 1. And again, we'll talk about that a little bit later. But make sure you know these shapes for these parent graphs. You should become familiar with them. And normally when we are graphing these, we don't always graph each of these points that we have in between. We usually look at certain key points. And what are key points on a graph? Well, key points are the maximum points of our graph. So this would be a key point up here, so maximums, intercepts, minimums. So in one wavelength, notice we have for cosine 1, 2, 3, 4, 5 key points, and for sine we have 1, 2, 3, 4, 5 points as well. And notice that those points are equally spaced apart. So for this part of our graph, we have our first key point here, 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 and here, and the spacing, if you notice in between, is equal. So when we're graphing these, we don't normally graph pi over 6, pi over 4, and pi over 3. We just usually stick to the key points. This is what we'll talk in the next part. So we'll come back to that kind of stuff in just a minute. So the sine and cosine and tangent graphs. If you'll recall, even functions are symmetric with respect to the y-axis. And algebraically, remember we showed that f of negative x was equal to f of x. So when you have symmetry with respect to the y-axis, remember you replace your x and y ordered pairs with negative x comma y, and that gives you the same thing back. For odd functions, it has symmetry with respect to the origin. And algebraically, f of negative x is equal to the negative of the function. And for origin symmetry, remember we replaced x and y with negative x and negative y. Now, we've talked about the unit circle before, and we've looked at this triangle that I have pictured here. It says when the coterminal side of theta is rotated counterclockwise about the origin, the values of x and y associated with the point P will change. For each value of theta, there's exactly one corresponding value for x, and then we have this set of ordered pairs for cosine and for sine that we can use. So remember that that point P of x comma y is really cosine comma sine. So cosine theta, sine theta, and normally we use t instead of theta, but since I have it in the problem, I'm going to leave it there. Now for this, that means if I do the cosine first, we get x is equal to cosine of theta, and we show that with the triangle and the unit circle. So for this, that means for my coordinate ordered pair, I would have theta comma the cosine of theta, and that's what I use in order to get my cosine graph. And for the sine graph, I have y equals the sine of theta. So in this case, I would get your angle comma the sine of that angle, which is your y value. That gives you your ordered pair. So you can also write that as theta comma y, because that's what we're really looking at on our unit circle. So this would be theta comma cosine theta and theta comma sine theta. Those allow us to graph the sine and cosine graphs. Now, we're not going to do this in our calculator just yet because we need to be able to do these by hand first, but when we do, you're going to have to be in radian mode. And I'll eventually show you guys how to do that. So now let's talk about the domain and period of sine and cosine. We can rotate around the circle an infinite many number of times. Therefore, the domain of sine and cosine function is going to be all real numbers, so negative infinity to infinity. The values of sine and cosine also range or oscillates from, so oscillates means just goes back and forth in between -1 and 1. If we add 2 pi, or 360 degrees, to each value of t in the interval from 0 to 2 pi, this completes a second revolution around the circle. Functions that behave in such repetitive or cyclic manner are called periodic. So that's something that we're going to talk about. The sine and the cosine functions are periodic functions with a period of, in this case then, when do they start repeating is what it means. So after every 2 pi or 360 degrees, we know that they're going to repeat the next wave. So the length of each cycle before it starts to repeat is the period of the function, and this is the horizontal distance. So the horizontal distance it takes to complete one wave before the graph starts to repeat. So one wave is equal to a cycle, which is equal to the period of your graph, which is important. Now, the period of your graph, we eventually will be changing, but for right now, for sine and cosine, we're going to stick with 2 pi. So if we look at this graph right here, we have y equals the sine of x, and I know it's the sine because it starts at 0. So it says how many periods are shown in this graph. So if I want to find the number of periods, I'm going to look to see how much one wavelength is before the graph starts to repeat. So from here to here would be one wavelength, and then notice that when we start here, we're back at 0, we're going up to 1, 0, -1, and back to 0, and that would be the second wavelength. So here are shown 2 cycles. If I continued and did another one, like so, that would be 3 cycles, and I could keep on continuing forwards to the right or to the left, backwards. So to sketch the basics graph of sine by hand, it helps to note the 5 key points in one period. And we already said that the key points are the intercepts, maximums, and the minimums. And these are nice because instead of, like I said, graphing pi over 6, pi over 4, pi over 3, it's just easier to graph all these key points that we have on our graph. So to get the key points, you take the period of the function and you divide it into 4 equal parts. Now, why would I divide it into 4 equal parts? If you think about your unit circle, which I'm just going to draw a circle over here. So if I think about this unit circle, notice that the sine graph is going to be 0 here at 0 radians, and then at pi over 2 radians right here, our graph is going to be 1 for maximum, 0, so that's an intercept. At 3 pi over 2, we get -1, and back around to 2 pi, we again get 0. So notice that these key points are happening in 4 equal parts on our unit circle. So in order to get the key points, you divide the period by 4. So let's take a look at the domain here. So the domain we know is going to be -infinity to infinity. The range is from bracket -1 to 1. And the period for this we just talked about was 2 pi. So the key points, whenever I'm graphing these, I'm going to take the period and divide it by 4, multiply it by 1/4, and so when I do that, I get 2 pi over 4, so that means my key points are going by pi over 2 in my graph. That's the interval in which I'm going to count by. So I always start at 0 for my sine graph, so 0, and notice I have pi over 2, and then this would be 2 pi over 2, which is pi, 3 pi over 2, and then 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2, and I just reduce it. And of course I can go backwards as well. Now those key points for your x-axis, I want to see each of those key points on your graph. That's why I have you guys list what the key points are, just the first interval that you're going by, and then you're just going to count from there. So then for my graph, we have x, and then we're doing, in this case, y equals the sine of x for my graph. So this would be the sine of x. So again, we always start with 0. And again, my key points for this graph, because they will be changing eventually when we make our cycles smaller or larger. So pi over 2, and then 2 pi over 2, which is pi, 3 pi over 2, and 4 pi over 2, which is 2 pi. And then you just have to evaluate. So the sine of 0 is 0. Pi over 2 would be 1, 0, -1, 0. So this is the first wavelength of the parent graph for sine. So this is the first wave before it starts to repeat itself. So we can of course keep going. So I know that if I look at my unit circle, we went all the way around my unit circle once, so we're back here at 2 pi. So then 5 pi over 2 would be up here, which would be a value of 1, and then 3 pi would be the next value, which would be here, and then 7 pi over 2 would be down here, and then back around would be back at 0. So notice my graph is going to continue just like it did for the first wavelength. And then, of course, I could keep on going backwards if I wanted to. So if I go backwards around my circle, I start at 0 and I go down here to negative pi over 2 would be -1. And then if I do negative pi, I have 0. negative 3 pi over 2 would be up here, which would be 1, and then back to negative 2 pi is 0. So my graph, oops, I went up too high. Didn't realize I did that. So my graph is going to look like this, and I didn't realize I did that on the other side as well. Sorry about that. So my graph is going to look like this. And of course, like we said before, we could keep going an infinite many times with positive angles or an infinite many times with negative angles. So the sine graph, if you look, has symmetry with respect to the origin, which makes it an odd function. And you can tell because for this, remember we said for odd functions, f of x, so if I do the sine of negative t, I should get the negative sine of t out. So remember we said we replace x and y with negative x and negative y. So if I have the point pi over 2 and 1, then notice down here I have negative pi over 2, negative 1. So the x and y's are now negative. So that's what makes it an odd function. For these next examples that we have right here, we're going to come back to those and we're going to skip that for right now, and we'll do that in class together. You can see if you can maybe try to do it on your own if you'd like, and then we'll talk about it in class. So let's go ahead and take a look at the cosine graph. So the cosine graph, I know that the domain is still the same, negative infinity to infinity. The range is from bracket negative 1 to 1. The period we talked about was 2 pi. So then the key points are going to be the period of your function divided by 4 equal parts. So 2 pi over 4 is pi over 2. So that means that's what my key points are going by. Every pi over 2, I have a maximum, a minimum, or an intercept. So for my graph, I have x and the cosine of that angle. So my first angle, we start off with this 0 radians, then pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. So the cosine of 0 radians would be equal to 1. The cosine of pi over 2 is 0. The cosine of pi is negative 1, 0, and then the cosine of 2 pi would be equal to a value of 1 again. So notice that now we have our graph starts up here. So this is the first wave, or the first cycle for my cosine graph. So notice it starts at 1 instead of starting at 0 and goes down first. So this is the shape that you should know for the first wavelength. And of course we could keep on going around our circle. So then I know that 5 pi over 2 is coterminal with pi over 2, 3 pi over 2 is coterminal with pi, 7 pi over 2 is coterminal with 3 pi over 2, and 4 pi is coterminal with 2 pi. So then we get our graph that looks like this. And of course we can go the opposite way. Negative pi over 2 would be coterminal with 3 pi over 2. And then negative pi would be here, which is coterminal with pi, and then 3 pi over 2, 2 pi. So my graph can go this way, and of course, like we said before, we could keep on continuing this way, or we could keep on continuing this way for our graphs an infinite many amount of times. But the first wavelength that we're interested in, that we usually look at first, is this from here to here, this distance, which is again one wave, or the first cycle. Now the cosine graph has symmetry with respect to the y-axis, which makes it an even function. And remember, even functions you can fold along the y-axis right here, and each side will match up, which it does in this case. And if I have the cosine of negative x, it's going to be equal to the cosine of x. And remember, we said if you have x, y in your graph, you should have negative x and then the same y value. So we have, in this case, pi right here, and this would be negative 1, so pi and negative 1. So I should have, in this case, negative pi, negative 1, which would be right here. So negative pi, negative 1. So that's what shows me that it's an even function. So if we look at this next graph, it says how many cycles or periods are shown. So when I'm looking at this graph, the first thing I ask myself is whether or not this is a sine or a cosine graph. The way that you can tell is where the graph is starting. So remember that our general shape for sine starts at 0 and goes like this. So this would be the sine of x, and if I do the cosine of x, it starts at 1 and then goes back up to a maximum, so this would be the cosine of x. So for this, I know that I look at that graph and it's starting up here at this value, so it looks like a cosine graph, so it's going down then up, so that would be one wave before it starts to repeat, and then we have the next wave right here, and then there's another one after that, and then we can go backwards. So it looks like we have 1, 2, 3, 4, 5 cycles or 5 periods shown. Notice that the cosine and sine graphs, like we said, have similar shape. It says how much does the cosine graph need to shift to become the sine graph. So maybe if you take a look at the graphs that we did previously, how much has my graph move over? So remember, these key points that we have on our graph are going by pi over 2. So this would be pi over 2. This right here is pi, and then we have 3 pi over 2, and this is 2 pi, and then down here we have 0, and then of course this right here would be pi over 2, and this would be pi. This right here is 3 pi over 2, and then back to the maximum would be 2 pi, so I know it's not a very good graph, but just in general. So if you look at these two graphs, notice that the sine and cosine graph, the difference between the two is a shift of pi over 2. So why don't you see if you can write the transformation for the sine and cosine graph, and then we'll talk about it in class. We'll also talk about these two examples right here in class as well. So see if you can answer them, and then we'll go over them. So let's go ahead and take a look at the last graph that we want to do. And so the last parent function that we need is the graph of tangent. So for the graph of tangent, recall from the unit circle that the tangent is equal to the values of y over x, which is sine theta over cosine theta. And remember, we said that tangent is undefined when your cosine, in this case, of theta is equal to 0, because we can't divide by 0, so those become, remember, when you have 0 in your denominator, vertical asymptotes. So asymptotes are going to appear at certain places on our graph. So let's think about from 0 to 2 pi. So from 0 to 2 pi on my unit circle, so here's my graph. Where is the cosine going to be 0? So cosine 0 here, and the cosine 0 is here. So first it's 0 pi over 2, and then we have 3 pi over 2. And then if we go, so we went here, down to here, and then we're going to go back up to here. So what would be the next value that we're hitting? The next value, well, if I add another pi, I would get 5 pi over 2, or yeah. Or 7 pi over 2, sorry. So we have 3 pi over 2 plus another pi, which would be 2 pi over 2. So 5 pi over 2, okay. So 5 pi over 2, and I could keep on going around my circle. I can also go in the negative direction, so negative pi over 2, negative 3 pi over 2, etc. So notice that we're hitting at odd multiples. So usually when we're going to write this out, we start with the first place that we have, which is pi over 2. So asymptotes appear at when theta is equal to, for cosine, pi over 2 plus every single, notice it's happening every single pi on my graph, so that's half my graph, half my graph, half my graph. So plus the amount it takes to get there, so pi times n, because we have odd multiples, so where n is an integer. So those are all the places where our asymptotes are going to appear at. And so for this, let's go ahead and start graphing this out. So on my graph, if I'm looking at it, I'm going to start graphing this one a little bit different. So my key points for sine and cosine go by pi over 2. It's different for tangent. The period of a tangent graph is pi. And so the key points for this one would be, instead of pi over 2, pi, your period, divided by 4. So pi over 4 is what I'm going to go by. So for this graph, notice that our asymptotes, so on my unit circle, are going to be every pi, and notice that we have right here, this distance on my graph is from negative pi over 2 to pi over 2, so I'm going to use that on here. So I have negative pi over 2, and if I put 0 in the middle, and then I have plus a pi over 4 would give me negative pi over 4. Plus pi over 4 is 0, plus pi over 4 would be pi over 4, and then plus another pi over 4 would be 2 pi over 4 or pi over 2. So these are the values I'm going to use. At negative pi over 2, we're undefined for tangent. The tangent of negative pi over 4 is negative 1. The tangent of 0 is 0. Tangent of pi over 4 is 1. And the tangent of pi over 2 is undefined. So remember that we've looked at these values before on our unit circle. So again, just to show you, remember we said that here we have 0. Here we have values that are undefined. And then this value right here for pi over 4 is 1, and this value is negative 1. So that's just using your unit circle. So for this graph, we always want to label everything on our x-axis that are our key points, what they're going by. So my first key point starts at pi over 4. Then we have pi over 2. And then the next one, we're going to keep going by adding another pi over 4. So 1 pi over 4, 2 pi over 4. The next one would be 3 pi over 4. And then we have 4 pi over 4. And then we have 5 pi over 4. And then the next one would be 3 pi over 2. And I can go backwards. Negative pi over 4 would be here. This would be negative pi over 2, negative 3 pi over 4, negative 5 pi over 4, and negative 3 pi over 2. And the next one, or sorry, I missed one, didn't I? Pi over 4, pi over 2, 3 pi over 4. I missed pi. I didn't realize that. So negative pi, negative 5 pi over 4, and then negative 3 pi over 2 would be out here. So I'm going to put the asymptotes on my graph first. So anytime you're doing tangent, you should always put your asymptotes on your graph. And then, of course, I have one out here at negative 3 pi over 2. So for my graph, if I start doing this at pi over 4, I have a value of 1. At the tangent of 0 is 0. The tangent of negative pi over 4 is negative 1. So I should label this 1 and negative 1. So my graph, I know, has these points connected. Now I need to figure out how the rest of it goes. So let's think about, again, our sine and cosine graphs. So my sine graph looks like this for the first wavelength, and my cosine graph looks like this. So if we look at pi over 2 on my sine graph, pi over 2 is a value of 1, because remember tangent sine over cosine, so sine over cosine. So because of that, my sine in this case, when we're approaching pi over 2, is 1, but for cosine, since we can't get 0, notice what are your cosine values doing? They're coming closer and closer to 0 from the positive direction, so we have 1 over a small number, and remember we've talked about before, when you have 1 over a small number, it's a very large number, and so that means that my graph is going to go from here and going to shoot up this way. Now we have the negative side of my graph, so if I continue down this way, right here would be negative pi over negative pi over 2. So in this case, for my value of sine, I have, in this case, just to go back, so when we have the negative pi over 4, we have the negative 1, which is what we're looking at, and then, so I meant to say that, and then negative pi over 2 is undefined. So looking at those values for the sine, though, notice the sine is following negative 1. The cosine is getting close to 0. So for that, the sine is getting negative 1 over something, a small number. And so because of that, it's equal to a very large negative number. And so that means that the rest of our graph is going to go down this way. And remember that your graph comes close to your asymptotes, but doesn't touch or cross over vertical asymptotes ever. And then our graph is going to keep on repeating. So at 3 pi over 4, I have -1. At pi, 0. 5 pi over 4 would be 1. And then my graph, again, is going to come up this way and go down this way. And then at -3 pi over 4, I have 1. Negative pi would be 0, and 5 pi over 4 would be -1. So my graph again continues. So this is what the parent graph for tangent looks like. And notice that instead of repeating every single pi, the distance between here and here, where it completes one wave before it starts to repeat, would be a distance of pi. So that's why the period for this function is pi instead of 2 pi. Now for this, one cycle then is going to complete itself in between the asymptotes, so -pi over 2 and pi over 2, which is why we get the period. If you'll notice then the tangent, we have pi over 4, 1, and -pi over 4, -1, so it's an odd function with respect to the origin. And the last thing it says, the graphs must contain dotted asymptotes lines. These lines will move if the function contains a horizontal, shift, stretch, or shrink. And the last thing we need to talk about is the domain. So the domain is going to be all real numbers except for these places where you have your asymptotes at. So I know it's all real numbers, but we can't have numbers equal to pi over 2 plus pi times n, where n is an integer. So for these graphs, make sure that you know what the parent functions look like. And again, those problems that we didn't get to we'll get to in class tomorrow.